or good afternoon, or good whenever you're watching this video. Anyway, today we're going to talk about 16.1, which is talking about vector fields. We're shifting away from real valued functions and integration and looking at vector functions. So our learning goals for today are to be able to describe a vector field with a function and to describe it with a graph, two different representations. We also want to define what a potential function is and what a gradient vector field is and the relationship between those two things. And then finally, the relationship. Given a potential function, we want to be able to find the gradient vector field, and given a gradient vector field, we want to be able to work backwards to be able to describe what that potential function was. So let's start off by describing a vector field. Notice that this is something that we've seen before, so it is a little bit of review, but we're going to go into a little more detail than what we did before. So let's say that we have a function, and typically when we have our vector functions, we always use capitals, letters to represent the function. So before, when we were talking about real valued functions, we would use little f's. And the inputs are going to be points in space, but our outputs are going to be vectors. And I'll write the formal notation and then I'll explain what this formal notation is even talking about. So here we have a capital F representing the function. We see that our inputs in this case are points in R2. That's important to point out. So I can pick any point on the xy plane. That's the input that's going to go into this function. And what do I get out? I get out a vector. And this vector is going to be described by two different component functions. So f1 we call a component function, and it's going to be a function of x and y. And f2 is another component function, and it's a function of x and y. And together, they make up a vector. So let's see an example for a little more clarity of what this looks like. For example, let's say that I have this vector field function, f of xy is equal to x squared y, comma, y minus 3x. So what's going on in this function? Inputs in this case are points, and our outputs in this, our x component function, which we usually call f1, is given by x squared y. So I will write that down. f1, which is a function of x and y, is equal to x squared y, and this is called our first component function. And similarly, our second component function, f2, is also a function of x and y, and it's given by y minus 3x. And this is our second component function. So I plug in a point, and what do I get out? I get out a vector. So this vector, this part of the component is telling me how far I'm going over in the x direction. This part is telling me how far up I'm going in the y direction, and it makes a tip-to-tail vector. And we'll see some examples of what they look like graphically in a second or two. One other thing that I want to add is that these functions that we have, these examples that I've given are just with two variables. We can also talk about three-dimensional vector fields. So in that case, my inputs would be x, y, and z, three different points, and my outputs would be f1, which is a function of x, y, and z, f2, which is a function of x, y, and z, and f3, which is also a function of x, y, and z, meaning that I could have inputs that are points in space in R3, and my output, instead of being a two-variable function or vector, would be a vector that has three. So for this example, let's look at a vector function where my inputs are in R2, so my points have x and y coordinates, and my output is a vector, and in this case the vector is given by a first component equal to y and a second component equal to x. We're going to analyze graphically what this vector field looks like. So in order to analyze it, we're going to start just by plotting some points. I'm going to plot inputs, which are points, and outputs, which are going to be vectors. So let's select a nice selection of input points. Typically, I'm just going to go around in a circle. Maybe I should pause the video, or you can go quickly through this part of the video. I'm going to pick points that I think are useful points for generating a picture of what's going on. Oh dear, maybe I'm going to run out of space. -1, 0. Okay, so maybe we fast forward through that part. So I've picked a collection of points that could be endpoints, and really we could pick any points that we wanted to plot. We just needed to be able to get an idea of what this vector field looks like. My inputs are points in R2, so in this case I'm putting the point 0, 0 into the function, and what do I get out? I get out where my y component is 0, and my x component is also 0. So I get out the vector 0, 0, which graphically I can't really represent because the arrow's not going anywhere. But for the next one, I see that if I input the point 1, 0, I get an output that's a vector where my y component is 0 and my x component is 1. So when I plot this on my graph, I'm going to have my base point, the input into this, be the point over 1 up 0. So here's my point 1, 0. And I'm getting out a vector that's 0 in the x direction and 1 in the y direction. So my vector is the vector 0, 1, emanating from this base point. Similarly, if my base point is 1, 1, the vector that I get out is 1, 1, because the y component is 1 and the x component is also 1. So with a base point starting at 1, 1, I plug in this vector and I see that the output is a vector of length 1 in the x direction and length 1 in the y direction. Now if I continue doing this for all of these points, I see that if I plug in the point 0, 1, I get the vector 1, 0. If I plug in negative 1, 1, I get 1, negative 1, and so on and so forth. And I'll just plug in and copy out what these points are going to be. Negative 1, 0, negative 1, 1. Sorry, that got a little twisted at the bottom there. Let's plot some of these on the vector field. So we left off here. Let's look at the point 0, 1 as my base point. The vector that emanates out of that goes 1 in the x direction and 0 in the y direction. So it's going this way in the x direction and it's not moving up at all. My next base point is negative 1, 1, which is a base point right here. And that vector goes 1 in this direction and negative 1 in this direction. But that base point, negative 1, 0, it goes 0 in the x direction and negative 1 in the y direction. Negative 1 starts right here. It goes negative 1 in the x direction and negative 1 in the y direction. A base point of 0, negative 1 gives me a vector that goes negative 1 in the x direction and 0 in the y direction. And then finally, at the point 1, negative 1, I go negative 1 in the x direction and 1 in the y direction. So I just plotted a bunch of vectors at a bunch of different base points, and even with this, I'm not sure if I have a great idea of what this vector field looks like. It gives me a sense for these vectors. If I were to continue onward and plot the ones and replace all of those ones with 2's instead, you'd see that your vectors would go in exactly the same direction. They would just be twice as long. So if I could compute this by hand, if I felt like it, I could do, let's see, this one will go twice as long this way. So this gives me a somewhat better idea, and if I were to graph a bunch more vectors, we would find that our vector field has vectors pointing inwards along this way with getting greater and greater magnitude, and they point sort of this way. Maybe this is now really messy, but they're going in quadrants 2 and 4, and they're going out in quadrants 1 and 3. And we'll investigate graphing these a little more when we get to our technology section.